Welcome back, students. Water and clouds. We've moved on from pressure, and now we're going to learn how air pressure makes clouds and rain. Here's the basics of what we're going to talk about. Where water came from, breakdown of water on the planet, water's phase change, latent heat, and humidity and relative humidity, and then we'll finish off looking at lifting mechanisms. Alright, so there's a lot of water on our planet. It covers about 70% of Earth's surface. And it's been debated back and forth, heck, where'd all this water come from on our planet? It turns out that most of it was released onto the surface of the planet by volcanism over the past 4 billion years. And that's why we have so much water on our planet. It was thought it was comets, but no longer. Here's an image. We do live in a water world. 71% of our Earth is covered with water. And coincidentally, it makes up 70% of your body. Yeah, that is water. Cool. Here's a breakdown of all that water. Obviously, most of it's in the oceans, 97%. Of the stuff that's fresh, the stuff that's on the surface is mostly in ice and glaciers. There's a tiny little bit in freshwater lakes, atmospheres, rivers, and streams. A decent amount in saline lakes. Then you got a lot in the ground, which is going to be relevant when we talk about the water project later on in class. Okay, so this is super duper, scooper duper important. Okay, water undergoes phase changes. Where our planet sits in relation to the sun, water can be in all three phases. It can be a solid, a gas, or a liquid. But this is what's neat. If you have a gas, water molecules, right? Oxygen, hydrogen, and that gas condenses into water. Do you see how you get less dense? Goes down here, and they're tighter together. They're flowing around, but they're not as like bouncing all over the place up here than they are down here. Well, to get them all close together like this, these molecules have to slow down. And if you slow down, it's like putting the brakes on your car. By stepping on the brakes, you put pads in your car that cause friction and release heat. So when water vapor goes to liquid water, boom, you release heat. That type of heat is called latent heat. The same is true as when you go from water to ice. When you freeze water, you'll release heat. It'll go, put on the brakes, it releases the heat. And the opposite is true. If you melt ice, okay, it takes heat, right? Because we got to speed up. These molecules got to go from this structure to moving around all liquidy. It takes latent heat to do it, and then it takes a lot of latent heat to jump up here to the water vapor area. The car analogy is if you're going to speed up, it takes gas. You got to put your foot on the pedal. That gas is the energy you need in order to go. Okay. You can also go from ice to water vapor and then water vapor back to ice. It's called sublimation. Obviously, if you're going to go from ice all the way to water vapor, you need a lot of energy to make that jump. And if you go from water vapor all the way down to ice, you release a lot of energy to go all the way down to ice. One other cool thing to notice is, if you notice how ice is structured, here's the oxygen and it has a bunch of hydrogens out on the outside to build the molecule. Okay. This is actually less dense than free-flowing water. So the water is all slushy. This is solid, but because of the way the crystal is structured in these kind of hexagons, it actually is more spread out and it's lighter. That's why ice floats on water. It's almost the only substance that does that, where the solid form is less dense than the liquid form. That's important because if that was not the case, ice wouldn't float on oceans. All that ice would fall down to the bottom, and most of our oceans would be big blocks of solid ice. Here's a cool look of that hexagonal structure of ice when it becomes solid. Snow crystals are actually formed from water vapor, going all the way from water vapor straight into ice. You can release a ton of latent heat when you do that, right? Because you got to slow down. Here's frost in your fridge. Same thing. Frost in your fridge. Most of you guys have freezers that don't have frost, but if you did, the water vapor goes straight from water vapor, boom, to ice, releases tons of latent heat into your freezer that then you have to pump out, pay electricity to do that. Kind of interesting. So this is the diagram you're going to want to know. And here I'm going to ask you to produce this diagram for me on their second exam. The key is you go from ice to water vapor. Energy gets absorbed because everything's going faster. We go from slow to moderate and moderate to fast. The opposite is the case when you go in the opposite direction. Energy is released, and specifically it's 540 calories to go from water vapor to water, 85 calories to go from water to ice. You need to know these numbers. By the way, that's per cubic centimeter of water. And these are just pretty pictures down at the bottom. Okay, now let's talk about humidity and relative humidity. Here's the deal. Let's say this is just a circle, an amount of air. Okay, it's 5 p.m. It's hot outside. The air's hot. The hotter the air mass, the more moisture that air mass can hold. So there's this amount of water vapor right there means you have a relative humidity of 20%. The water vapor is filling up 20% of what this air mass could hold of water vapor. At 11 o'clock, when it was a lot cooler, do you see how the ability for that air mass to hold moisture has shrunk? We haven't changed the water vapor. Water vapor has stayed the same, but the water vapor now fills up a lot more of what that air mass can hold. Now we're at 50% relative humidity. At 5 a.m., it's matching perfectly. The air mass is saturated. The air mass cannot hold any more water vapor, and that's because at 5 a.m. you have the coldest time of the day. That's oftentimes when dew forms, hence that will give us dew point temperature down here in a second. Okay, so relative humidity is how much water vapor content is in the air, like this, divided by the capacity, divided by that, and then times 100 just gives you a percentage. Okay, that's relative humidity. Actual humidity is this amount, how much water vapor is actually in some volume of air. We're not going to worry about that. All we're focused on is relative humidity. The key thing is the hotter an air mass gets, the lower the relative humidity. The colder the air mass gets, the higher the relative humidity. Dew point temperature, that's the temperature at which an air mass cools to reach 100% relative humidity. Okay, so if we took this air mass and you cooled off and cooled off and cooled off, cooled off until you have 100% relative humidity, exactly at that temperature, when you have perfectly filled in the circle, that's your dew point temperature. It's called the dew point temperature because typically the coldest time of the day is around 5 a.m. and if you go outside at that point, you'll see dew on the grass. And that's because the air has cooled to the dew point where you have 100% relative humidity, and at that point water gets forced out of the air mass. And so here's a general relationship. As you go throughout the day, here's your temperature. As you get higher in temperature, you get lower relative humidity. And then as you cool off, you get higher relative humidity. So they tend to be mirror images of each other. Here is a glass of water. Right, so here we have a glass with ice cubes in it, and it's very cold on the outside. And you see this in Phoenix a lot, especially right now, and well, for me right now, but in the monsoon seasons when we have high relative humidity, that when the outside air comes in contact with your cold drink, at least on the outside, boom, that water gets chilled to the dew point temperature and past the dew point temperature, well past 100% relative humidity, and so water gets forced from being a water vapor, is forced to condense into water, and you get the water dripping all over the outside of your glass. Okay, this water does not come from inside your glass. What's interesting, in the wintertime, you can have a glass that's sitting there and you'll have no condensation on the outside, and that's because the dew point temperature is below freezing, below 32 degrees Fahrenheit, and this water can't get colder than 32 degrees, therefore you don't get any condensation. And the last thing I'll say is, if we have condensation, if we're taking the water out here as water vapor and we cool it down when it touches the glass into water where it's moving slower, right, we release latent heat. Heat is actually being released off of that glass. Okay, so how much water does air hold? Here's a graph. It's actually very simple, but here's the gist. Here at 0 degrees Celsius, about 32 degrees Fahrenheit, an air mass can only hold 4 grams of water per kilogram of air, so not very much. But then as you warm up, if you get up here into Phoenix temperatures, right, you can hold a whole bunch of water. And that kind of makes sense, because our monsoon storms this time of year, right, if you cool off this air mass from, say, 100 down to 80, boom, you've lost a lot of water, okay? huge amount of water. You'll get these big, intense storms. But down here where it's cold, the rainstorms, they can be significant, but they're not going to be as intense as they are up here where it's hotter. And then what's kind of interesting is once you get down here to the super cold, -20, -10, or 0 degrees in Fahrenheit, right? You can't have a big storm. You can't have a big snowstorm. There's no moisture in the air. It's all more or less gone. Okay, so now we're going to talk about what makes an air mass rain. To do that, we need to understand forces that act on an air mass, the dry and wet adiabatic lapse rates, forming clouds and cloud types, the 4 lifting mechanisms, and then the orographic exercise, frontal exercise, are things we're going to do in lab. Okay, so forces that act on an air mass. So here's our air parcel just sitting out there, and it can either be buoyant or gravity can act on it. If it's buoyant, typically it's going to be hotter than the surrounding air, and it'll rise, and therefore it'll be buoyant. If it's colder than the surrounding air, it's going to be denser, and it will sink. So higher the density, gravity acts on it, it falls. Lower the density, it's buoyant, it lifts. Okay? Then it's written down for you down there at the bottom. Okay, adiabatic lapse rates. So here's the general idea. As you get higher in elevation, that's all this graph is telling you. So here's temperature, here's elevation. As you get higher in elevation, you get the dry adiabatic lapse rate. That's what DAR stands for, dry adiabatic lapse rate of 10 degrees Celsius per 1,000 meters, or 5.5 degrees for every 1,000 feet. We're going to simplify that and just call that 5 degrees every 1,000 feet. So what that means is as we get higher in elevation, we cool off 5 degrees Fahrenheit for every 1,000 feet that you go up. Right now you're at 1,500 feet. Flagstaff is at 7,000 feet. We can just say it's at 7,500 feet. So it's 6,000 feet higher. 6 times 5, it should be roughly 30 degrees cooler up in Flagstaff. Okay, but that is again a rough approximation. Okay, because then we have to account for the moist adiabatic lapse rate. We have DAR, the dry adiabatic lapse rate, but then we also have the moist adiabatic lapse rate. And so this is what's neat. As an air mass lifts off the surface, it's going to cool at 10 degrees Celsius for every 1,000 meters. Okay, but then once you hit the dew point temperature, something switches. So the air is lifting, right? If it's lifting, it's a low pressure. We're cooling off, we're cooling off, we're cooling off. Then all of a sudden we hit the dew point temperature. Then at this point, and instead of 6, we're going to use 5 degrees Celsius for every 1,000 meters. We start cooling off at 5 degrees Celsius every 1,000 meters. Okay, we're only going to cool off half as much up here than we were down here. Because we're inside this giant cloud, we only cool off half as much. Why is that? Well, that's because you're taking water vapor and turning it into water droplets that make up the cloud. That releases latent heat, and it heats up the entire cloud. Okay, it heats it up. And therefore, as your air mass gets higher, technically it is cooling 10 degrees Celsius every 1,000 meters, but then there's 5 degrees Celsius that's being added to it from latent heat. So the net is it only cools off 5 degrees Celsius for every 1,000 meters. Okay, it's not cooling off as much. But also as a result, that means it ends up being much warmer than the surrounding air. It gets very buoyant and wants to continue lifting, and that's how you get storms. Also notice, see how the bottom of the cloud is flat? A lot of clouds, the bottom is actually very, very flat. That's because that's your dew point temperature. That's the point at which you reach 100% relative humidity. Boom, hit the bottom of the cloud. It's flat. Now at that point, you're squeezing the water vapor out of the cloud and forming water droplets in the cloud. Sweet. Okay, now we need to talk about unstable air and stable air. I'm actually going to do the bottom one first. Stable air is simple. All it means is here's an air parcel that's 25 degrees. As it rises, it cools off at the dry adiabatic lapse rate of 10 degrees Celsius per 1,000 meters. So it goes up 1,000 meters, it cools off 10 degrees, so now it's 15 degrees Celsius. But the surrounding air that it rose into is warmer. It's 20 degrees. Now this air is cooler. If it's cooler, it's going to be denser. It's just going to fall back down again. So you just get this circulation of air in this area because of the rate at which it's cooling. Unstable air is when an air mass is or becomes warmer compared to the surrounding air, it takes off. Okay, so in this case, as we cool off, right, the surrounding air ends up being colder, so we stay warmer and we keep lifting. And then eventually we'll hit 100% relative humidity, we'll hit the dew point temperature, you're going to start to release latent heat, and that'll keep it even warmer, and that's how you generate storms. Okay, unstable air masses are always associated with storms. Here's a cool image, right? So here's a bottom of a cloud that's flat, right? So the air down here, it's rising, it's cooling off, boom, right at that point, it reaches 100% relative humidity. That's your dew point temperature for this air mass. At that point, you start to condense water droplets into the cloud. It's very unstable. As you're releasing that latent heat, the air is warmer than the surrounding air. Buoyancy will act on it, and then it takes off. And you get that look at the top of that cloud, it just looks like it's shooting off into the upper atmosphere because it's very unstable. Okay? And eventually, this cloud is going to generate rain. Let's talk about that. So, forming rain is actually kind of neat. You have to take these cloud droplets. So you need dust particles in the atmosphere for the cloud droplets to condense on. They form these little tiny drops. But as the storm intensifies, those drops hit each other, and they get bigger and bigger and bigger and bigger. Then eventually that unstable air mass, that low pressure air that's pushing it up, it can't keep a drop this big aloft. And eventually the drops this big, boom, will start to fall out of the cloud. And that's how you eventually will generate rain. Over here there's a bunch of cloud types that can generate rain or that don't generate rain, like these upper ones up here. I'm not going to test you on these, just so you know they exist. The big cool ones are cumulus nimbus. Those are the ones that generate rain. Blood rains, which is kind of interesting. You can generate blood rains. They tend to happen in Europe. And you get blood rains when this condensation nuclei is like a red dust coming out of the Sahara Desert. And that will dye the droplets red color, and so it will rain red, which I'm sure was a bad sign if you were an emperor or a king back in the day. There is also a blood rain that can happen in Spain because the cicadas out there, or the locusts, will poop this kind of red poop, and then the poop floats into the air. It forms a condensation nuclei, and you generate this real super blood poopy bug rain, that sounds gross. Okay, so now the 4 lifting mechanisms. So this is the 4 main ways in which you're going to lift an air mass to cool it off and generate rain. That's what we've been building towards. To get rain, you got to take an air mass. It needs to be low pressure so the air lifts. When that air lifts, it needs to cool off at a rate such that it stays warmer than the surrounding air. And so it wants to keep lifting. Eventually, because as it cools off, its relative humidity gets higher and higher till eventually it'll reach 100% relative humidity. It'll hit the dew point temperature. At that point, well, water vapor will condense and start forming a cloud. That's why you have the bottom of the clouds that are flat. That cloud will then take off. You're pumping out latent heat, which makes it even more unstable. The cloud gets bigger and bigger. The cloud droplets start smacking into each other, and you get rain. But fundamentally, at the start, you need a lifting mechanism. You need to lift the air. And the 4 ones are convergent, convectional, orographic, and frontal. I would pause the video and write these down. Convergent is air flows towards low pressure like the tropics. Convectional is heating over the continental surface. Orographic is when air hits a mountain. And frontal is when cold air hits warm air. Or warm air hits cold air. So here's some images for you. Convergent. Just write in your notes. Convergent is the same as the ITCZ, the Intertropical Convergent Zone. It's the most dominant low pressure on the planet, and it generates a ton of rain. It gets its own lifting mechanism. The other one is more local. It's convectional. It's local heating. They have this diagram done over open field where you have a bunch of dirt. Dirt has low thermal inertia. It gets very hot. That's why you get dust devils over these fields. It can kick off a storm when that warm air lifts. You can have air that hits a mountain. You can have a high pressure over here, low pressure over here. As that wind comes in and hits the mountain, it's forced to lift up and over. and you'll generate a storm as a result, just because the air is being forced up and over the mountain. And then you can have warm air that slams into cold air. That warm air, boom, is forced aloft. Basically, the cold air will act like a mountain in that regard because the two air masses won't mix. This is too light and fluffy. This is too cold and dense. Here's a picture of Earth from space. You can see these series of clouds here. This is your example of convergence. This is the ITCZ that's raining over the tropics of Africa, that's lifting and forming clouds and raining all along this area. Convectional. Florida right here is basically this stick of land into the Gulf of Mexico, which is a warm body of water, that the warm, moist air over the Gulf of Mexico will go over the land. The land heats up during the day, that air lifts, and boom, they get tons of rainstorms in the summertime. And actually, Florida gets more thunderstorms and lightning than any other place in the United States. Orographic, we're going to be doing this in the lab, so I'm not going to worry about it too much. All these scary numbers will make sense. We'll show you how this works. This is kind of cool. This is Nevada with a series of mountain ranges in Nevada. We'll learn later why Nevada has over 100 mountain ranges in it. Looks like a bunch of caterpillars going down the state. But then if you compare it to the rainfall data for the state, you can see that the mountains kind of perfectly line up for where it gets rain, and that's because of that orographic effect of those air masses slamming into those mountain ranges. Frontal air masses, we'll go into more detail about this in the lab, but the general idea is we have cold air to the north, tends to be dry. We got warm air to the south, it tends to be humid, Gulf of Mexico, Gulf of California, South Pacific. When these air masses collide, you get a frontal system. So here's an example of a frontal system. We have a high pressure here, right? Anticyclonic flow. The winds go out, deflect to the right. And then those winds head on over and they want to spiral into the low. They want to go straight in, but they get deflected to the right. But the deal is, this high pressure is pulling cold air. Right here, it's pulling all this cold air from Canada down. So we have this huge wedge of cold air getting pulled down. Down here on the low pressure, we're pulling in air into the low pressure from the Gulf of Mexico. Right? It's warm and moist. As this air is moving in, it gets hit by this rushing cold air, and it gets, boom, lifted up and over dramatically, and you're going to get rain all along that front. We also get warm fronts, but we're not going to worry too much about warm fronts. Here's another look at it. Here's Denver, Colorado. If you look at this, and I'll explain this in lab, this is a weather station. But it has 78 degrees as temperature, 69 degrees dew point. So these dew points are really high. So this is warm, moist air, and the air is heading in this direction. But then if you look at Denver, dew points have dropped to 46 and temperature is 47, so it's much colder here. This cold front came sweeping down and smashed into this warm air heading up into this low, and you're generating a tons of rain all along that warm front. Cyclogenesis is just the process of all this beginning. So it starts out with kind of spread out, the cold fronts over here, the warm fronts over here. Here's the example of warm front. This is just where the warm air gets pushed up over slower cold air below it. So it's kind of a ramp that the warm air rises up. But eventually this cold air is going to rush in and capture that warm front, and the two zipper up, and they zip into what's known as an occluded front. Here's a picture of what a cold front looks like from the side. Here's that warm, moist air heading that direction, gets hit by the cold, dry air, boom, gets lifted, big storm. Warm front is where warm air basically starts right up the back of cooler air mass below. That's passive, it isn't really doing anything. You'll generate rain, but it doesn't tend to be very big. I'm not going to focus on warm fronts in this class because we very rarely get warm fronts here in Phoenix. Okay guys, we've made it to the things to know list for this lecture. I need you guys to understand the source of water on Earth and its general geographic breakdown, the water phase changes and latent heat energy transfer, relative humidity and the general breakdown throughout the day, the buoyancy and gravitational forces on an air mass, The dry and wet adiabatic elapse rate, and I'll just state them for you. The dry that I want you to know is 10 degrees Celsius per 1,000 meters. The wet is 5 degrees Celsius per 1,000 meters. The four lifting mechanisms, convergent, convectional, orographic, and frontal. This know the math part we're going to talk about in lab. Cold fronts, primarily. Warm fronts, not really. And the dominant air masses. All right, guys. Hope you had a good time. I'll see you in class.